Welcome, everyone, to a crucial discussion on building robust software systems. Today, we're diving into basic error handling for tasks, a topic often overlooked until a system is already in crisis. In the world of distributed applications, from managing user requests to processing batch jobs, failures aren't just possibilities, they're certainties. The true mark of a professional-grade system isn't its ability to avoid errors entirely, but how elegantly it recovers and maintains stability when things inevitably go wrong. By the end of this lesson, you'll gain practical insights and a clear understanding of how to implement foundational error handling. You'll learn to identify why robust error handling is your system's best friend, grasp the core concept of controlled failure, understand the key architectural components involved, and see how to seamlessly integrate these mechanisms into your existing task execution flows. This knowledge will empower you to transform your applications from fragile prototypes into resilient, production-ready components that can withstand the unpredictable nature of real-world operations. Let's be honest, in complex, distributed systems like a large social network's background job processor or a major e-commerce platform's order fulfillment engine, failures are not edge cases, they're everyday occurrences. A database connection might time out, an external API could return a 500 error, or a worker node might simply run out of memory. Without proper error handling, these minor hiccups don't just stop a single task, they can cascade into system-wide outages. Imagine a scenario where a task scheduler processes thousands of jobs. If just a few tasks hang indefinitely due to an unhandled exception, they tie up valuable resources, creating a backlog, and eventually bringing the entire system to a halt. This is why error handling acts as your system's safety net. It ensures that even when an individual component or task fails, the entire system can gracefully continue operating, preventing those small issues from becoming catastrophic. It's about recognizing that every task, regardless of what goes wrong, must reach a definitive final state. At the heart of resilient task execution is the principle of controlled failure. This simply means that every task execution must result in a clear, trackable outcome. Whether a task succeeds or fails, your system should know exactly what happened and update the task status accordingly. This gives you immediate visibility into your system's health, prevents failed tasks from indefinitely consuming resources, and maintains data integrity. It's about moving away from tasks hanging in an ambiguous running state towards a definitive succeeded or failed status. This approach integrates seamlessly with a task status state machine, transitioning a task from running to failed when an exception occurs. This embodies the fail-fast principle. Instead of letting tasks linger and consume resources, we quickly detect failures and move them to a terminal state. This keeps your task queue healthy and provides immediate feedback for troubleshooting, allowing your teams to address issues proactively rather than reactively. It's a fundamental shift from hoping things don't fail to gracefully managing when they do. To implement this controlled failure, we typically rely on three key architectural components. First, an exception wrapper, usually a try-catch block, surrounds your core task logic to intercept any runtime exceptions. Second, a failure recorder updates the task status to failed and stores all the critical error details in your database for debugging. And third, a status transition manager ensures these updates are atomic, preventing race conditions that could lead to inconsistent states. When a task begins execution, our enhanced executor follows a precise control flow. It first marks the task as running, then wraps the actual task logic in that comprehensive try-catch block. If successful, the status updates to succeeded. If an exception occurs, it captures the error details and updates the status to failed. Crucially, a resource cleanup step ensures the executor thread is released regardless of the outcome. The critical insight here is that the status update operations themselves must be bulletproof. If the task logic fails, but the status update also fails, you're back to an inconsistent state, losing the very visibility you sought to gain. This structured approach ensures reliability. We've covered a lot today, laying the groundwork for truly resilient systems. Remember, implementing proper error handling ensures resilient task execution, transforming your scheduler from a fragile prototype into a production-ready component that can withstand the unpredictable nature of real-world operations. We learn to embrace controlled failure and the fail-fast principle, moving tasks to a definitive terminal state quickly, which drastically improves visibility and resource management. We also identified the core components, the exception wrapper, failure recorder, and status transition manager, and walked through the robust control flow that governs task execution and status updates. You'll know your error handling is working when no tasks remain in a running status indefinitely, your monitoring dashboards show clear failure rates, and investigations take minutes instead of hours. This foundation is critical. It prepares us for more sophisticated patterns, like automatic retry mechanisms, which we'll explore in future lessons. By clearly marking tasks as failed with detailed error information, you gain the ability to implement intelligent retry logic, distinguishing between temporary glitches and permanent issues. So, for your self-assessment, how does robust error handling prevent system outages and improve operational efficiency? Reflect on the concepts we've discussed and consider how you'd apply them in your own projects. Thank you.